In the depths of space, an object from beyond our solar system has been putting on a show that has astronomers around the world checking their calculations twice. 3I Atlas, an interstellar visitor that first caught our attention months ago, has been behaving in ways that challenge everything we thought we knew about comets. What started as routine observations of another space rock has evolved into something far more intriguing, with December 19, 2025 marking a critical date that could reshape our understanding of what travels between the stars. If this mystery has you as captivated as it has the scientific community, make sure to hit that subscribe button and ring the notification bell so you don't miss any updates as this story unfolds. Drop a comment letting me know where you're watching from and what you think about these latest developments. Your engagement helps us bring you more content like this, so thank you for being part of this journey into the unknown. The story begins with what should have been a straightforward observation. When 3I Atlas was first detected, it appeared to be following the playbook of every interstellar visitor we'd encountered before. These cosmic wanderers typically arrive from the void between stars, swing around our sun in predictable arcs, and disappear back into the darkness. We've seen this dance twice before with objects like Oumuamua and Comet Borisov, each teaching us something new about the materials and processes that exist in other stellar systems. But 3I Atlas decided to rewrite that playbook entirely. As it approached its closest point to the Sun on October 29, 2025, something unprecedented began to unfold. Instead of the modest activity we'd expect from a comet warming up under solar radiation, 3I Atlas erupted into a display of energy that has left researchers scrambling for explanations. The numbers tell a story that shouldn't be possible. Recent observations have revealed jets of material stretching nearly 3 million kilometers into space behind this object. To put that distance into perspective, that's roughly 8 times the distance between Earth and our Moon. These aren't the gentle puffs of gas and dust we typically see from comets. These are massive, sustained streams of material being expelled with tremendous force and precision. Even more puzzling are the jets pointing toward the Sun, fighting against the relentless outward pressure of solar radiation and the solar wind. In the normal physics of comets, material gets blown away from the Sun, not toward it. Yet here we have streams of particles maintaining their coherence across nearly 1 million kilometers, while pushing directly into the solar headwind. This defies every model we have for how comets should behave. The energy requirements for this display are staggering. According to calculations by Harvard astrophysicist Avi Loeb, 3I Atlas is losing mass at a rate of approximately 50 billion tons per month. That's not a typo. We're talking about 50 billion tons of material being expelled every single month. For a natural comet to sustain this level of activity through simple ice sublimation, it would need to be several times larger than what our best observations suggest. This creates what scientists call an energy budget problem. Every physical system has to balance its books. The energy going out must be accounted for by energy coming in, or being stored somewhere. For 3I Atlas, the mathematics simply don't add up using conventional comet physics. It's like watching a campfire that's somehow consuming an entire forest, while appearing to burn only a single log. The Hubble Space Telescope has provided us with size estimates for this object, and when we compare those measurements to the observed level of activity, we encounter a fundamental contradiction. Either our instruments are wrong about its size, or something else entirely is powering this spectacular display. Neither possibility is comfortable for astronomers who prefer their observations to align neatly with established physics. What makes this situation even more extraordinary is the structure and timing of these jets. They're not the chaotic random bursts we'd expect from natural outgassing. Instead, they appear organized, almost engineered in their precision. Multiple distinct streams are firing in specific directions, maintaining their coherence over vast distances and showing a level of coordination that has never been documented in any comet before. The timing of this activity is equally puzzling. While we'd expect peak performance around the object's closest approach to the Sun, 3I Atlas has continued its intense display well after that point. Most comets show declining activity as they move away from solar heating, but this visitor seems to be maintaining or even increasing its output weeks later. It's as if some internal process is driving the show, independent of external solar influence. This brings us to December 19, 2025, the date that has astronomers around the world marking their calendars. On this day, 3I Atlas will make its closest approach to Earth at a distance of approximately 270 million kilometers. While that's far too distant to pose any collision risk, it represents our best opportunity to determine what exactly we're dealing with. The observations planned for December 19th will be crucial for answering fundamental questions about this visitor. Most importantly, will 3I Atlas arrive as a single intact object, or will we discover that it has fragmented into multiple pieces? This distinction could determine whether we're looking at an unusual but natural phenomenon, or something that challenges our basic assumptions about what travels between the stars. If the object has broken apart under the intense stresses of its solar encounter, we'd expect to see a dispersed debris field with multiple fragments following slightly different trajectories. This would suggest that natural forces overwhelm the structural limits of what was essentially a very unusual comet. While spectacular, this scenario would fit within our current understanding of physics, even if it pushed the boundaries of what we thought possible. However, if 3I Atlas arrives on December 19th as a coherent, intact object still producing those massive jets, we'd be forced to confront far more challenging questions. How could any natural body maintain structural integrity while expelling material at such extraordinary rates? What energy source could sustain this level of activity for months? And perhaps most unsettling, what does it mean if these jets represent not random outgassing, but controlled propulsion? The implications extend far beyond academic curiosity. If 3I Atlas turns out to be something other than a conventional comet, it would represent our first confirmed encounter with technology from beyond our solar system. This possibility, however remote, has captured the attention not just of astronomers, but of government agencies and military analysts who understand that such a discovery would fundamentally alter our place in the universe. The scientific community approaches this possibility with appropriate caution. Extraordinary claims require extraordinary evidence, and the default assumption remains that we're observing natural phenomena, however extreme. But the accumulating evidence from 3I Atlas continues to strain conventional explanations. Each new observation adds another piece to a puzzle that doesn't quite fit together using the tools we currently have. Consider the jets themselves. Their structure suggests something far more organized than random sublimation. They maintain distinct boundaries, travel in specific directions, and show patterns that resemble controlled thrust rather than chaotic venting. The sunward-pointing streams in particular would require velocities far exceeding what natural outgassing typically produces. We're talking about exhaust velocities more consistent with rocket engines than ice turning to vapor. The composition of the expelled material adds another layer to the mystery. Spectroscopic analysis reveals an unusually high concentration of carbon dioxide, making up approximately 87% of the detected gases. This is far different from the water-dominated composition we see in typical comets. While not impossible for a natural object, it suggests formation in an extremely cold environment, possibly in the outer reaches of another star system or even in interstellar space itself. But composition alone doesn't explain the behavior. The real puzzle lies in the energy management. Natural comets heat unevenly, with the sun-facing side becoming much warmer than the shadowed regions. This temperature gradient drives the sublimation process and creates the pressure that forms jets. For 3I Atlas, however, the energy seems to be distributed and channeled with remarkable efficiency, as if some mechanism is actively managing the thermal environment. This level of thermal control doesn't occur naturally in known materials. It would require either exotic compounds with properties we've never encountered, or active systems capable of redistributing energy across the object's structure. Neither explanation fits comfortably within conventional comet science, yet both remain more palatable than acknowledging we might be observing technology. The broader context makes this mystery even more significant. 3I Atlas is our third confirmed interstellar visitor, following Oumuamua in 2017 and Comet Borisov in 2019. Each of these objects has been different, suggesting that interstellar space contains far more diversity than we initially assumed. Oumuamua was inert and rocky, showing no signs of typical comet activity. Borisov appeared completely normal, behaving exactly as our models predicted. Now 3I Atlas presents us with extreme activity that challenges our understanding of what's physically possible. This pattern raises uncomfortable questions about detection bias. Are we only seeing the most unusual interstellar visitors because they're the ones that catch our attention? How many normal, quiet objects might pass through our solar system unnoticed? And perhaps more importantly, If artificial probes do travel between stars, would we recognize them when we see them? The December 19th observations will involve telescopes around the world and in space, representing one of the most comprehensive study campaigns ever mounted for a single object. High-resolution imaging will search for signs of fragmentation or structural changes. Spectroscopy will analyze the composition and velocity of the continuing jets. Precise astrometry will track any deviations from purely gravitational motion that might indicate active propulsion. The results of these observations will shape not just our understanding of 3I Atlas, but our approach to future interstellar visitors. If we confirm that this object represents natural processes pushed to previously unknown extremes, we'll have learned valuable lessons about the diversity of materials and conditions in other stellar systems. If we find evidence suggesting artificial origin, we'll face the profound realization that we're not alone in our ability to send objects between the stars. As December 19th approaches, the astronomical community is preparing for either outcome. New detection systems are being designed to spot future visitors earlier in their approach, giving us more time to study them before they disappear back into the cosmic dark. International protocols are being discussed for how to handle data that might suggest non-natural origins, and researchers are developing new theoretical frameworks that can accommodate the extreme behaviors we're observing. The story of 3I Atlas is far from over. Whatever we discover on December 19th will be just the beginning of a longer investigation that could extend for months or years. If the object fragments, we'll track the debris and study how it disperses through the solar system. If it remains intact, we'll continue monitoring its trajectory and activity as it recedes toward interstellar space, stellar space. What sets this investigation apart from previous astronomical mysteries is the sheer scope of international coordination required. Space agencies across the globe have quietly reallocated resources, redirecting some of their most sensitive instruments toward this singular target. The European Space Agency's solar observation satellites have been repurposed to track 3I Atlas from multiple angles simultaneously. NASA's Deep Space Monitoring Network has cleared observation schedules to ensure continuous coverage. Even amateur astronomers with backyard telescopes are contributing data points to what has become the most distributed scientific effort in recent memory. The technical challenges of December 19th extend beyond simply pointing telescopes at the right coordinates. The object will be moving at tremendous velocity relative to Earth, requiring precise tracking algorithms to maintain focus. Its brightness could vary unpredictably if fragmentation occurs, demanding rapid adjustments to exposure settings and filter configurations. Most critically, the window for optimal observation is limited. Weather, equipment failures, or data processing delays could mean missing crucial details that might not be observable again for decades. Behind the scenes, a more complex drama is unfolding. Government agencies have been briefed on the possibilities, though the exact nature of these discussions remains classified. Military satellite tracking systems have been tasked with providing backup observations. The rhetoric from official sources has been carefully measured, emphasizing scientific curiosity while downplaying more speculative interpretations. This calculated approach reflects an understanding that public reaction to extraordinary findings could be unpredictable. The physics community itself has become divided into camps with distinctly different interpretations of the available data. Conservative researchers maintain that exotic but natural processes must explain 3I Atlas behavior, pointing to gaps in our understanding of comet composition and thermal dynamics. They argue that invoking artificial origins is premature and potentially damaging to scientific credibility. Every unusual astronomical phenomenon, from pulsars to fast radio bursts, has ultimately found natural explanations once sufficient data was gathered. Progressive voices, however, point to the accumulating evidence that seems to resist conventional interpretation. The mathematical precision of the jet orientations, the sustained energy output far exceeding theoretical limits, the apparent thermal management that defies known material properties. These researchers don't claim certainty about artificial origin, but they insist that the possibility deserves serious consideration rather than reflexive dismissal. The debate has spilled into academic conferences and peer review processes, creating unusual tensions within institutions typically characterized by collegial disagreement. Papers addressing 3I Atlas have faced extended review periods as referees struggle with how to evaluate claims that push against the boundaries of accepted science. Some journals have reportedly delayed publication of certain analyses pending the December 19th observations, preferring to wait for additional data rather than contribute to speculation. Meanwhile, the engineering implications haven't been lost on propulsion researchers. The jet characteristics observed in 3I Atlas align remarkably well with theoretical predictions for advanced plasma propulsion systems currently under development in terrestrial laboratories. Multiple universities have filed patents in 2025 for superconducting magnetic containment engines that could, in principle, produce exhaust patterns similar to what we're witnessing. This convergence between observed phenomena and cutting-edge human technology adds another layer of complexity to the interpretation challenge. The plasma physics involved in these advanced propulsion concepts operates on principles that are well understood but technically demanding to implement. Magnetic fields can confine and accelerate ionized gases to velocities far exceeding those possible with chemical rockets. The energy requirements are substantial, but not impossible for a sufficiently advanced power source. If such a system were operating in 3I Atlas, it would explain both the high exhaust velocities needed to maintain jets against solar wind pressure and the apparent thermal management that keeps the object structurally intact. Detection networks beyond traditional astronomy have been quietly monitoring for additional signatures. Radio telescopes scan for any structured emissions that might indicate communication or data transmission. Military radar installations track for objects that might separate from the main body. Gravitational wave detectors analyze their data for perturbations that could reveal the object's true mass independent of optical observations. This multi-spectrum approach reflects an understanding that if 3I Atlas is indeed artificial, its technological signatures might extend beyond the visible phenomena. The psychological preparation for December 19th extends throughout the scientific community and into government planning circles. Contingency protocols exist for various discovery scenarios, though their specific details remain confidential. Academic institutions have prepared carefully worded statements for different possible outcomes. International communication channels have been established to coordinate information sharing and prevent conflicting public announcements that could fuel misinformation. Public interest has grown steadily as fragments of information leak through social media and astronomy forums. Amateur sky watchers have been attempting their own observations, sharing images and speculations that sometimes outpace official announcements. This grassroots engagement represents both an opportunity and a challenge. Citizen scientists can contribute valuable data points and maintain public interest in space exploration. However, premature or inaccurate interpretations can also create noise that complicates scientific communication. The historical precedent for this level of scrutiny of a single astronomical object is limited. While events like Comet Hale-Bopp or the Shoemaker-Levy 9 impact-generated public fascination, neither carried the potential implications for our understanding of intelligence in the universe that 3I Atlas presents. The closest parallel might be the SETI searches for extraterrestrial radio signals, but those efforts have been characterized by negative results rather than positive phenomena demanding explanation. What makes December 19th particularly significant is the binary nature of the primary question. Either 3I Atlas has fragmented into a debris field, or it hasn't. Either we'll see clear evidence of structural failure consistent with extreme natural processes, or we'll observe continued coherent behavior that challenges conventional explanations. Unlike many astronomical mysteries that unfold gradually over years or decades, this one promises relatively definitive resolution within a matter of hours. The fragmentation scenario would provide closure of sorts, confirming that we're dealing with natural phenomena pushed to extraordinary limits. A dispersed debris field would demonstrate that no material, however exotic, can withstand the forces involved in producing jets of this magnitude for extended periods. This outcome would be scientifically valuable, teaching us about the mechanical limits of interstellar objects and the processes that govern their destruction. It would also be psychologically comfortable, fitting within our existing framework of understanding. The survival scenario opens far more complex possibilities. An intact nucleus continuing to produce organized jets would demand explanations that stretch or break our current models. Natural processes capable of such sustained, controlled energy release remain theoretical at best. The alternative explanations venture into territory that astronomy has traditionally avoided. The possibility that some objects traveling between stars are products of intelligence rather than chance. instrument calibration for December 19th has reached unprecedented levels of precision. Every telescope, spectrometer, and detector that will contribute to the observations has undergone multiple verification cycles. Cross-referencing protocols ensure that any unusual readings can be confirmed across multiple independent systems. The scientific community understands that extraordinary claims require extraordinary evidence, and that evidence must be bulletproof against both technical criticism and institutional skepticism. The data analysis procedures have been established with similar rigor. Multiple independent teams will process the same raw observations using different algorithms and assumptions. Results will be cross-checked before any public announcements. This methodical approach reflects hard-learned lessons from previous astronomical controversies where preliminary findings were misinterpreted or sensationalized before proper peer review could occur. As December approaches, 3I Atlas continues its outbound journey, its jets still visible to our most sensitive instruments, despite the increasing distance from the Sun. The consistency of this activity, maintained well beyond the point where solar heating should have declined significantly, adds to the puzzle that December 19th observations must resolve. Whatever powers this display has shown remarkable persistence, suggesting either exotic materials with properties unlike anything in our experience, or active systems capable of sustained operation across months of interplanetary travel. The questions surrounding 3I Atlas have evolved from simple curiosity about an unusual comet to fundamental inquiries about the nature of intelligence and technology in our galaxy. If this object proves to be artificial, it would represent confirmation that other civilizations have achieved interstellar travel capabilities. If it remains natural despite its extreme behavior, it would demonstrate that the universe contains processes and materials far stranger than we currently comprehend. Either outcome would reshape our understanding of our place in the cosmos. The countdown to December 19th has begun, and with it, humanity approaches what could be one of the most consequential observations in the history of astronomy. The universe is about to deliver its verdict on whether we've been witnessing the death throes of an exotic comet or our first encounter with technology from beyond the solar system. The weeks leading up to December 19th have revealed additional layers to the 3I Atlas mystery that few anticipated. While the world's attention remains focused on the upcoming close approach, new data emerging from monitoring stations across the globe suggests that this object's behavior has entered an entirely different phase. The jets that initially captured our attention have begun exhibiting patterns that defy every computational model astronomers have developed for predicting comet activity. Advanced spectroscopic analysis conducted throughout November has uncovered something that has researchers quietly sharing encrypted communications. The material being expelled from 3I Atlas shows chemical signatures that don't align with any known repository of interstellar compositions. The carbon dioxide that dominates the expelled gases carries isotopic ratios that fall outside the range documented in our solar system or in meteorite samples from other stellar regions. These ratios suggest either formation conditions unlike anything we've previously encountered, or processing through mechanisms that remain completely unknown to current astrophysics. The isotopic anomalies extend beyond simple compositional differences. When analysed in detail, the expelled material shows evidence of what can only be described as molecular organisation. Complex carbon chains appear in concentrations that natural sublimation processes shouldn't produce. These compounds require specific temperature and pressure conditions to form, conditions that don't exist in the random thermal environment of a typical comet. Yet here they are, streaming away from 3I Atlas in quantities that suggest deliberate chemical processing rather than accidental formation. Thermal imaging from multiple infrared telescopes has revealed another unprecedented characteristic. Instead of the expected temperature gradient from hot sunward side to cold shadow side, 3I Atlas displays what appears to be active thermal regulation. Hotspots migrate across its surface in patterns that correlate with jet activity, as if heat is being deliberately redirected to specific regions. This level of thermal management requires either materials with thermal conductivity properties that exceed anything in our periodic table, or active systems capable of moving energy around the object's structure. The most disturbing development involves timing correlations that emerged only after months of continuous observation. The jet activity doesn't just respond to solar heating in the expected delayed fashion. Instead, it appears to anticipate changes in solar radiation intensity. Flares and coronal mass ejections from the Sun trigger corresponding changes in 3I Atlas behaviour, but these responses begin before the solar events could possibly have reached the object's location. This suggests either a monitoring capability that extends far beyond the object itself, or predictive algorithms sophisticated enough to model solar activity in real time. Ground-based radar installations have contributed data that complicates the picture further. Pulses directed toward 3I Atlas return with echo patterns that don't match solid body reflections. Instead, the returns suggest internal structure with multiple density layers and possibly hollow regions. Natural comets typically show uniform density profiles with some variation due to ice and rock distribution. The radar signature from 3I Atlas resembles engineered structures with distinct compartments and what could be interpreted as internal channels or conduits. Gravitational analysis using pulsar timing arrays has provided the most unsettling data yet. Several pulsars in the direction of 3I Atlas trajectory showed minute timing perturbations consistent with a gravitational source, but the mass calculations don't align with optical size estimates. The gravitational signature suggests an object roughly 10 times more massive than its visible dimensions would indicate. This mass discrepancy points toward either incredibly dense materials concentrated in a small volume or a much larger structure that remains largely invisible to our detection methods. The international coordination required for December 19th observations has revealed fractures in the usually collaborative astronomical community. Certain government agencies have requested data-sharing restrictions that some researchers find unprecedented for civilian scientific observations. Military satellite tracking networks have been repositioned to provide redundant coverage, ostensibly for backup observations but raising questions about what specific information might be considered sensitive. These operational security measures suggest that decision-makers at the highest levels are preparing for outcomes that extend beyond academic interest. European Space Agency communications, obtained through Freedom of Information requests, reveal internal discussions about containment protocols and information management strategies. While the specific details remain redacted, the tone suggests preparation for discoveries that could have broad societal implications. References to controlled disclosure procedures and impact assessment frameworks indicate that the potential for extraordinary findings is being taken seriously at institutional levels that typically focus on budget allocations and mission scheduling. The physics underlying 3I Atlas behavior has attracted attention from researchers normally focused on theoretical propulsion systems. Several teams working on fusion ramjet concepts and magnetic plasma confinement have published analyses suggesting that the observed jet characteristics match theoretical predictions for advanced interstellar propulsion systems. These papers, while carefully worded to avoid direct claims about artificial origin, demonstrate that human engineering is approaching capabilities that could produce similar phenomena. The convergence between observed behavior and theoretical technology creates an uncomfortable parallel that few are willing to discuss openly. Orbital mechanics specialists have identified another anomaly that adds to the growing list of unexplained characteristics. 3. I-Atlas trajectory shows microcorrections that appear to compensate for perturbations before they fully manifest. Small gravitational influences from Jupiter and Saturn, which should gradually alter the object's path over months, seem to be countered by precisely timed adjustments in jet orientation and intensity. This level of trajectory management requires predictive modelling capabilities and response systems that operate on timescales much faster than natural sublimation processes typically allow. The energy budget calculations have become increasingly problematic as more data accumulates. Even accounting for exotic volatile compositions and optimal thermal efficiency, the sustained power output required to maintain current jet activity exceeds what any known energy storage or generation mechanism could provide over the observed time span. Chemical energy from molecular bonds falls short by orders of magnitude. Radioactive decay, while longer lasting, occurs at rates too slow to explain the rapid response characteristics we observe. This leaves only more exotic possibilities like controlled nuclear processes or energy sources that current physics doesn't adequately describe. Amateur radio operators monitoring frequencies around 3I Atlas have reported structured signals that don't match natural electromagnetic phenomena. While these reports remain unconfirmed by professional observatories, the consistency of descriptions across multiple independent observers suggests something beyond random noise. The signals appear to pulse in patterns that correlate with jet activity cycles, as if the electromagnetic emissions and physical expulsions are components of a coordinated system. Official responses to these reports have been dismissive, but private communications between researchers suggest more serious investigation is ongoing. The December 19th observation campaign has expanded beyond traditional astronomical instruments to include experimental detection systems normally used for classified defense applications. Synthetic aperture radar arrays designed for satellite tracking have been reconfigured for deep space observation. Quantum interference detectors developed for gravitational wave research have been oriented toward 3i Atlas position. These specialized instruments offer detection capabilities that extend far beyond conventional telescopes, potentially revealing characteristics invisible to standard astronomical observation methods. Data security protocols for the December 19th observations have reached levels typically reserved for national security operations. Multiple encryption layers protect data transmission between observatories. Physical access to control rooms has been restricted to essential personnel with security clearances. Real-time analysis will occur in isolated computing environments with no network connectivity to prevent unauthorized data leakage. These measures suggest an expectation that the observations could produce information considered sensitive by government agencies, with interest extending beyond scientific curiosity. The psychological preparation within the astronomical community reflects awareness that December 19th could mark a fundamental shift in how we understand our place in the universe. Senior researchers have privately expressed concerns about maintaining scientific objectivity when confronting data that challenges core assumptions about natural versus artificial phenomena. Younger scientists, less invested in existing theoretical frameworks, appear more open to extraordinary interpretations but also more susceptible to premature conclusions based on incomplete data. This generational divide adds another layer of complexity to what is already the most scrutinized observation campaign in modern astronomy. Public interest has intensified as December 19th approaches, driven partly by information leaks and partly by growing awareness that something unprecedented is unfolding. Social media discussions range from measured scientific speculation to elaborate conspiracy theories about alien visitation and government cover-ups. This public attention creates pressure for rapid disclosure of findings, while simultaneously demanding careful verification to prevent misinformation from overwhelming actual data. The balance between transparency and accuracy has become a central concern for institutions managing the observation campaign. The backup systems established for December 19th reflect understanding that equipment failures or atmospheric interference could compromise the primary observation sequence. Redundant telescopes have been positioned at multiple geographic locations to ensure coverage regardless of local weather conditions. Data recording systems have been duplicated and distributed across multiple facilities to prevent loss of critical information. Communication networks have been established with automatic failover capabilities to maintain coordination between observation sites even if primary systems fail. As December 19th approaches, 3i Atlas continues its outbound journey with jet activity that shows no signs of declining, despite increasing distance from solar energy sources. The persistence of this behavior well beyond the point where natural processes should have exhausted available volatile materials adds urgency to the upcoming observations. Whatever mechanism drives this extraordinary display has demonstrated remarkable longevity and consistency, characteristics that point toward either exotic physics we don't yet understand or engineered systems designed for extended operation in the harsh environment of interplanetary space. The questions that December 19th observations must address have expanded far beyond simple comet classification. We need to determine whether we're witnessing natural phenomena pushed to previously unknown extremes, or our first confirmed encounter with technology from beyond our solar system. The implications of either answer will reshape fields ranging from astrophysics to astrobiology, potentially influencing government policy, international relations, and humanity's understanding of its significance in the cosmic context. The final countdown has begun toward what may prove to be the most consequential day in the history of astronomical observation. December 19th, 2025 will either confirm that the universe contains natural processes far stranger than we imagined, or provide evidence that intelligence capable of interstellar travel has visited our solar system. Either outcome promises to transform our perspective on existence itself, marking the moment when humanity's relationship with the cosmos changed forever. The international space community has been operating under protocols that haven't been tested since the Cold War era. Communication channels between major space agencies now include encryption methods typically reserved for military intelligence. The December 19th observation window represents more than a scientific milestone. It's become a stress test for humanity's ability to process information that could fundamentally alter our understanding of reality itself. Technical preparations have revealed just how unprepared our detection infrastructure really is for this type of phenomenon. The instruments designed to study distant galaxies and stellar phenomena aren't optimized for tracking objects that behave unpredictably at relatively close range. Engineers have been working around the clock to recalibrate systems, adjust tracking algorithms, and coordinate timing between facilities that were never meant to operate as a unified network. The challenge extends beyond hardware limitations. Data processing systems designed to handle routine astronomical observations are struggling with the volume and complexity of information streaming from 3i Atlas. The object generates data signatures that don't fit standard classification algorithms. Pattern recognition software, trained on decades of comet and asteroid observations, produces error messages when attempting to analyze 3i Atlas behavior. This forces researchers to develop new analytical frameworks in real time, essentially building the tools they need while the phenomenon they're studying continues to evolve. Financial implications have begun affecting research institutions worldwide. The resources required to maintain continuous monitoring of 3i Atlas exceed the annual budgets of most observatories. Emergency funding allocations from government agencies have kept the observation campaign operational, but these expenditures raise questions about sustainability if similar objects appear in the future. The astronomical community is confronting the reality that studying potentially artificial interstellar visitors requires infrastructure investments that dwarf traditional research budgets. Security considerations have introduced complications that few scientists anticipated. Data from 3i Atlas observations now flows through classification review processes before reaching peer-review journals. Research teams find themselves signing non-disclosure agreements for projects they initially considered routine scientific investigations. The boundary between open scientific inquiry and national security concerns has become blurred in ways that make many researchers uncomfortable, while simultaneously acknowledging the potential implications of their findings. The December 19th observation protocol includes contingencies for discoveries that could trigger immediate government intervention. Automated systems will flag certain types of data patterns for expedited review by security agencies before scientific analysis can proceed. These protocols exist in classified documents that most of the researchers participating in the observations haven't seen. The tension between scientific transparency and security concerns creates an atmosphere of uncertainty about how findings will be handled and disclosed. International cooperation faces unprecedented challenges as different nations approach the 3i Atlas phenomenon with varying levels of openness and paranoia. Some countries have restricted access to their most sensitive detection equipment, limiting the scope of collaborative observations. Others have insisted on independent verification of all data before sharing results. The scientific ideal of open collaboration encounters the reality that potential evidence of extraterrestrial technology carries implications that extend far beyond academic interest. The media management strategy for December 19th reflects careful consideration of how extraordinary findings might be received by the general public. Press releases have been prepared for multiple scenarios, with language carefully crafted to inform without causing panic or premature speculation. The challenge lies in communicating complex scientific uncertainties while acknowledging the profound implications of various possible outcomes. Scientists trained to discuss measurement errors and statistical significance must now consider how their words might affect global stability and public confidence in scientific institutions. Backup observation sites have been established in remote locations with minimal electromagnetic interference and optimal atmospheric conditions. These facilities operate with skeleton crews and autonomous systems designed to continue functioning even if primary observation centers experience technical failures or other disruptions. The redundancy reflects understanding that December 19th represents a singular opportunity that cannot be repeated if primary systems fail at crucial moments. The psychological preparation extends beyond the scientific community to include counselors and communication specialists who understand the potential societal impact of confirming artificial origin for 3I Atlas. Support systems have been established for researchers who might struggle with the implications of their findings. The possibility that humanity is not alone in developing interstellar travel capabilities challenges fundamental assumptions about our uniqueness and significance in the universe. These philosophical and psychological dimensions require preparation alongside the technical aspects of observation. Advanced simulation systems have been running continuously, attempting to model every possible scenario for what December 19th observations might reveal. These simulations include not just the physics of potential fragmentation or continued coherence, but also the sociological and political ramifications of different discovery outcomes. The models help decision-makers prepare for scenarios ranging from confirmation of exotic but natural phenomena to evidence of artificial intelligence operating beyond our solar system. The energy signature monitoring has intensified as 3I Atlas approaches its closest point to Earth. Multiple wavelength observations across the electromagnetic spectrum have revealed patterns that don't match any known natural processes. The consistency of these patterns suggests either remarkable self-organization in natural systems or active control mechanisms that maintain specific operational parameters despite changing environmental conditions. This level of stability across varying solar radiation intensities and gravitational influences points towards sophisticated regulatory systems. Quantum interference patterns detected in radio observations of 3I Atlas have attracted attention from physicists working on advanced communication technologies. The patterns resemble theoretical predictions for quantum-encrypted data transmission across interstellar distances. While natural quantum effects can occur in space environments, the coherence and structure observed around 3I Atlas exceed what random processes typically produce. These observations remain preliminary and require confirmation from December 19th data to determine their significance. The trajectory analysis has revealed micro-adjustments that occur with timing precision that natural outgassing cannot explain. These course corrections happen at intervals that suggest either remarkable coincidence or active navigation systems responding to gravitational influences before they significantly affect the object's path. The mathematics of these adjustments indicate predictive capabilities that would require computational resources and sensor systems far exceeding anything in current human technology. Atmospheric disturbance patterns in Earth's upper atmosphere have begun showing correlations with 3I Atlas activity cycles. While the object remains millions of kilometers away, sensitive magnetosphere monitoring equipment detects minute fluctuations that align with the rhythmic patterns observed in the object's jet emissions. These correlations suggest that 3I Atlas influence extends beyond its immediate vicinity, possibly through electromagnetic fields or particle streams that interact with Earth's magnetic environment at levels just barely detectable by our most sensitive instruments. The December 19th observation timeline has been choreographed with precision that rivals military operations. Every telescope, spectrometer, and detector participating in the campaign will follow synchronized protocols designed to maximize data collection. While minimizing conflicts between different observation requirements, the coordination involves facilities across multiple continents operating on different time zones, requiring communication systems that maintain split-second timing accuracy across global distances. Contingency plans for equipment failures include rapid deployment of backup systems and real-time switching between primary and secondary observation platforms. Mobile telescopes have been positioned at strategic locations with the ability to quickly relocate if atmospheric conditions or technical problems compromise primary sites. The backup systems include experimental instruments not typically used for astronomical observations, including synthetic aperture radar arrays and quantum sensors developed for fundamental physics research. The data analysis pipeline for December 19th incorporates artificial intelligence systems trained specifically on 3I Atlas behavior patterns. These AI tools can process incoming observations in real time, flagging anomalies and potential artificial signatures faster than human analysts could identify them. The machine learning algorithms have been trained on theoretical models of both natural comet behavior and hypothetical artificial propulsion systems, allowing rapid classification of observed phenomena into categories that help guide immediate follow-up observations. Public interest monitoring systems track social media discussions and news coverage to gauge public readiness for different types of announcements. Communication specialists analyze public sentiment and prepare targeted messaging strategies for various discovery scenarios. The goal involves informing the public accurately while preventing panic or misinformation that could complicate official responses to extraordinary findings. These preparation efforts reflect understanding that December 19th could produce information that challenges public assumptions about humanity's place in the universe. The final equipment checks scheduled for December 18th include calibration procedures that exceed normal operational requirements. Every system participating in the observation campaign will undergo verification tests to ensure optimal performance during the critical observation window. These preparations include backup power systems, redundant data recording capabilities, and communication links that can maintain coordination even if primary networks experience disruptions. International agreements governing the sharing and disclosure of December 19th. Findings remain classified, but their existence suggests that world leaders recognize the potential significance of what might be discovered. These agreements presumably address how different types of findings would be announced, what information would be shared publicly versus kept confidential, and how international cooperation would continue if 3i Atlas proves to be of artificial origin. The countdown continues toward December 19th, with 3i Atlas maintaining its extraordinary behavior patterns despite increasing distance from the Sun. The object's persistence in producing massive, organized jets of material well beyond the point where natural sublimation should have ceased adds urgency to the upcoming observations. Whatever mechanism drives this phenomenon has demonstrated remarkable endurance and consistency, characteristics that point toward either physics we don't understand or engineering we haven't achieved. Weather monitoring systems across the globe track atmospheric conditions at every major observation site, with meteorologists providing hourly updates on cloud cover, atmospheric turbulence, and visibility conditions. Backup sites in different climate zones stand ready to assume primary observation responsibilities if weather compromises optimal observation locations. The December 19th window allows for some flexibility in timing, but atmospheric conditions could significantly impact data quality if primary sites experience adverse weather. The scientific community has prepared for multiple outcome scenarios, each requiring different types of follow-up investigations and public communications. If 3i Atlas is fragmented, researchers will focus on tracking debris patterns and analyzing the physics of structural failure under extreme conditions. If the object remains intact and active, the investigation will shift toward understanding propulsion mechanisms and energy sources that exceed current theoretical frameworks. Either outcome promises to advance our knowledge significantly, but the implications vary dramatically. December 19th approaches with the weight of history pressing upon every researcher, engineer, and analyst involved in the observation campaign. The data collected during those crucial hours could confirm that we live in a universe far stranger than we imagined, or provide the first evidence that intelligence capable of interstellar travel has visited our solar system. The questions that have driven months of investigation will finally receive answers that will shape humanity's understanding of its place in the cosmos for generations to come. The universe has delivered 3i Atlas to our doorstep at a moment when our technology is just barely capable of studying it properly. This convergence of cosmic timing and human capability suggests that we stand at a threshold, ready to learn truths about reality that previous generations could only imagine. December 19th will determine whether we're ready for those truths and what we'll do with them once they're revealed. The final preparations for December 19th have revealed just how much this single observation has transformed the global astronomical community. Research facilities that typically operate in quiet isolation now find themselves part of a coordinated network spanning continents and involving resources that would normally be reserved for detecting gravitational waves or mapping the cosmic microwave background. The scale of this undertaking reflects not just scientific curiosity, but an acknowledgement that we may be approaching one of the most significant moments in human history. Advanced computer modeling systems have been running continuous simulations, attempting to predict every possible outcome for what we might observe when 3i Atlas reaches its closest approach. These models incorporate thousands of variables, from the object's structural integrity under various stress conditions to the dispersal patterns we'd expect if catastrophic fragmentation occurs. What emerges from these calculations is a stark binary. Either we'll witness the spectacular death of an exotic comet, or we'll confirm that something far more extraordinary has been travelling through our solar system. The fragmentation models paint a clear picture of what natural breakup would look like. Computer simulations show that if 3I Atlas has indeed reached the limits of its structural integrity, we should see a debris field spreading across millions of kilometres. The largest fragments would follow trajectories close to the original path, while smaller pieces would disperse based on their size and the forces acting upon them. This debris cloud would continue expanding for months, creating a gradually dimming smear of reflected sunlight that our telescopes could track until the fragments become too small and distant to observe. But the survival scenario presents challenges that push against the boundaries of known physics. For 3I Atlas to remain intact while continuing its extraordinary display of activity would require explanations that don't exist in our current scientific framework. The energy requirements alone exceed what any natural process should be able to sustain. We're talking about power outputs that would drain the chemical energy stored in an object this size within days or weeks, not the months of sustained activity we've already observed. The material science implications are equally problematic. No known substance could maintain structural coherence while expelling material at the rates we've measured. The thermal stresses, mechanical forces, and radiation exposure should have torn apart any conventional comet long before reaching this level of activity. Yet here we are, watching 3I Atlas maintain not just its integrity, but what appears to be controlled, organised behaviour that defies every model we've developed for how interstellar objects should behave. International space law has been quietly examined by legal experts as governments consider what protocols might apply if December 19th confirms artificial origin. The Outer Space Treaty of 1967 addresses the exploration and use of space by nations, but contains no provisions for encounters with technology from other civilizations. Legal scholars have been working behind closed doors to develop frameworks that could govern such a discovery, including questions of jurisdiction, study rights, and information sharing requirements that could apply to evidence of non-human intelligence. The technical coordination required for December 19th has exposed limitations in our global space monitoring infrastructure that few anticipated. Telescopes designed for specific research programs don't easily integrate into coordinated observation campaigns. Data formats vary between institutions, communication protocols differ across agencies, and timing synchronization becomes critical when every second of observation could provide crucial information. Engineers have been improvising solutions to make systems work together that were never designed for this level of cooperation. Deep space tracking networks normally used for communicating with interplanetary missions have been reconfigured to monitor 3I Atlas with unprecedented precision. These systems can detect position changes measured in kilometers across distances of hundreds of millions of kilometers, providing the accuracy needed to distinguish between natural drift and active course corrections. If 3I Atlas is indeed under some form of control, these measurements could reveal the subtle adjustments that would indicate ongoing navigation rather than passive trajectory following. The spectroscopic analysis planned for December 19th will examine the expelled material with resolution capabilities that can identify individual molecular species and their relative abundances. This detailed chemical fingerprinting could reveal whether the jets contain compounds that require specific formation conditions or processing methods. Natural sublimation produces predictable mixtures of gases based on the original ice composition. Artificial propulsion systems would likely show very different chemical signatures, potentially including exotic compounds or unusual isotopic ratios that don't occur in natural materials. Electromagnetic monitoring has been expanded to cover frequencies far beyond the visible spectrum that typical astronomical observations focus on. Radio telescopes will search for any structured signals that might indicate communication or data transmission. Infrared detectors will map thermal signatures that could reveal internal heat sources or energy distribution patterns. Ultraviolet sensors will track ionization levels that might suggest electrical activity within the expelled material. This comprehensive electromagnetic survey aims to capture any non-optical signatures that could indicate artificial systems in operation. The gravitational analysis will provide perhaps the most definitive test of 3I Atlas' true nature. By measuring how the object's gravity affects the trajectories of nearby dust particles and gas molecules, researchers can determine its actual mass distribution. Natural comets have relatively uniform density with some variation due to ice and rock content. artificial objects might show very different internal structures, potentially with dense components concentrated in specific regions or hollow sections that would create distinctive gravitational signatures. Timing measurements during December 19th will achieve precision levels that can detect velocity changes measured in centimeters per second. This sensitivity could reveal whether 3I Atlas is making micro-adjustments to its trajectory that would indicate active propulsion rather than purely ballistic motion. Natural outgassing creates thrust, but in random directions that tend to average out over time. Controlled propulsion would show systematic velocity changes that correlate with specific operational patterns. The observation protocol includes automated systems that will flag any anomalies for immediate human attention. Machine learning algorithms trained on both natural comet behavior and theoretical artificial propulsion signatures will process incoming data in real time, alerting researchers to patterns that require immediate follow-up observations. These AI systems can identify subtle correlations between different types of measurements that human analysts might miss during the intense observation period. Backup communication systems ensure that critical findings can be shared between observation sites, even if primary networks experience failures. Satellite communication links, military communication channels, and even amateur radio networks have been configured to maintain connectivity between research facilities. The redundancy reflects understanding that December 19th observations might produce information too important to risk losing due to communication system failures. The psychological preparation has extended beyond the scientific community to include government officials and military personnel who might need to respond to extraordinary findings. Briefing materials have been prepared that explain the technical aspects of the observations and the potential implications of different outcomes. These educational efforts aim to ensure that decision-makers can understand the significance of whatever is discovered without requiring advanced degrees in astrophysics. Public communication strategies have been developed for multiple scenarios, with carefully crafted language designed to inform without causing panic or premature speculation. Press releases exist in draft form for outcomes ranging from confirmation of exotic natural phenomena to evidence suggesting artificial origin. The challenge lies in communicating scientific uncertainty while acknowledging the profound implications that various discoveries could have for humanity's understanding of its place in the universe. Security protocols for data handling reflect the sensitive nature of potential findings. Information classified as potentially significant will be reviewed by multiple independent teams before public release. This process aims to ensure accuracy while preventing premature disclosure of preliminary results that might be misinterpreted or sensationalized. The balance between scientific transparency and responsible communication has become a central concern for institutions managing the observation campaign. The final equipment calibrations scheduled for December 18th will verify that every system is operating at optimal performance levels. These checks include not just the primary observation instruments, but also the data recording systems, communication networks, and backup power supplies that keep the entire operation functioning. The calibration procedures exceed normal operational requirements because the December 19th observations represent a singular opportunity that cannot be repeated if technical problems compromise data quality. Weather contingency plans have been activated at observation sites worldwide, with meteorologists providing continuous updates on atmospheric conditions that could affect observation quality. Cloud cover, atmospheric turbulence, and precipitation all impact the ability of ground-based telescopes to collect high-quality data. Backup sites in different climate zones stand ready to assume primary observation responsibilities if weather conditions compromise the planned observation locations. The international coordination has created unprecedented cooperation between institutions that normally compete for resources and recognition. Rival research groups have shared equipment, expertise, and personnel to ensure the success of the December 19th observations. This collaboration reflects understanding that the potential significance of what might be discovered transcends individual institutional interests and national boundaries. Advanced data analysis systems have been configured to process the expected flood of information from dozens of instruments simultaneously. The computing power required to analyze spectroscopic data, imaging sequences, gravitational measurements, and electromagnetic signatures in real time exceeds the capacity of most individual research institutions. Distributed computing networks have been established to handle the computational load. with processing power donated by institutions worldwide. The observation timeline has been synchronized to account for the rotation of the Earth and the optimal viewing angles from different geographic locations. As 3i Atlas moves through its closest approach, different telescopes will have optimal viewing conditions at different times. The coordination ensures continuous coverage throughout the critical observation period, with seamless handoffs between facilities as the Earth's rotation changes, which locations have the best viewing angles. Emergency response procedures have been established for scenarios where observations might reveal immediate threats or require rapid follow-up measurements. Mobile telescope systems can be deployed quickly to locations with optimal viewing conditions. Communication protocols exist for coordinating international responses to unexpected discoveries. These contingency plans reflect understanding that December 19th might produce findings that demand immediate action rather than leisurely scientific analysis. The final countdown approaches as 3i Atlas continues its outbound journey, still producing the massive jets that have puzzled researchers for months. The object's behavior has remained remarkably consistent, showing none of the typical decline in activity that natural comets exhibit as they move away from solar heating. This persistence adds urgency to the December 19th observations and reinforces the critical importance of determining whether we're dealing with natural phenomena or something far more extraordinary. The questions that have driven this investigation will soon receive definitive answers. December 19th will either confirm that the universe contains natural processes far stranger than we previously imagined, or provide evidence that intelligence capable of interstellar travel has visited our solar system. Either outcome promises to transform our understanding of reality itself, marking a moment when humanity's relationship with the cosmos changed forever. The stage is set, the instruments are calibrated, and the world waits. In just days, we'll know whether 3i Atlas represents the most exotic comet ever observed, or our first confirmed encounter with technology from beyond the solar system. The universe has brought this mystery to our doorstep at precisely the moment when we possess the tools necessary to solve it. What we discover will echo through history, defining how future generations understand their place in a cosmos that may be far more populated and active than we ever dared to imagine. The preparatory phase for December 19th has reached its final stages, with research teams around the globe conducting last-minute equipment checks and system verifications. The complexity of coordinating dozens of observatories across different time zones and weather conditions has created logistical challenges that dwarf typical astronomical observation campaigns. Every telescope, spectrometer, and data recording system must function flawlessly during the narrow window when 3i Atlas reaches optimal viewing position. The technical specifications required for these observations push many instruments beyond their designed operational parameters. Telescopes built for studying distant galaxies must now track a rapidly moving object with unprecedented precision. Spectrometers calibrated for stellar analysis need reconfiguration to capture the unique signatures of expelled material traveling at extraordinary velocities. Even the most sophisticated detection equipment struggles with the data volume and complexity that 3i Atlas generates. Behind the scientific preparation lies a parallel effort involving government agencies and security organizations that rarely interact with civilian astronomy. The potential implications of December 19th findings have triggered protocols designed for situations that extend far beyond academic research. Classification review, processes, information sharing agreements, and communication security measures, more typical of military operations, now govern what was initially considered routine scientific observation. The energy calculations surrounding 3i Atlas have become increasingly problematic as researchers attempt to balance observed behavior with known physics. The sustained power output required to maintain jet activity at current levels exceeds every theoretical framework for natural energy sources. Chemical energy from molecular bonds falls short by enormous margins. Radioactive decay operates too slowly to explain the rapid response patterns observed. This leaves only exotic possibilities that challenge fundamental assumptions about what's possible in natural systems. Advanced computer modeling has explored every conceivable natural explanation for 3i Atlas behavior. Exotic ice compositions, unusual internal structures, thermal runaway processes, and electromagnetic effects have all been incorporated into sophisticated simulations. While some models can partially explain individual aspects of the observed phenomena, none successfully account for the complete range of characteristics displayed by this object. The mathematical frameworks consistently point toward energy management and structural control that exceeds natural capabilities. The international space law implications have attracted attention from legal experts who typically focus on Earth-based territorial disputes rather than cosmic jurisprudence. The existing framework of space treaties and international agreements contains no provisions for encounters with technology from other civilizations. Legal scholars have been quietly developing new frameworks that could govern the study and potential interaction with evidence of non-human intelligence should December 19th confirm such extraordinary findings. Electromagnetic monitoring systems have detected patterns in the radio frequency spectrum around 3I Atlas that don't match any known natural phenomena. These signals appear structured rather than random, with repetitive elements that suggest either remarkable self-organization in natural processes or active transmission systems. The patterns correlate with visible jet activity, as if electromagnetic and physical emissions are components of a coordinated operational system rather than separate random events. The trajectory analysis has revealed microcorrections that occur with timing precision that natural outgassing cannot explain. These course adjustments happen at intervals suggesting either extraordinary coincidence or navigation systems capable of predicting and compensating for gravitational influences before they significantly affect the object's path. The mathematics indicate computational capabilities and response systems that would require technology far exceeding current human achievements. Gravitational wave detectors, normally focused on detecting collisions between black holes and neutron stars, have been reconfigured to monitor for any spacetime disturbances that might indicate exotic propulsion systems. While no clear signals have emerged, the sensitivity of these instruments could potentially detect gravitational anomalies associated with advanced technology operating at scales we don't yet understand. The absence of such signals doesn't rule out artificial origin, but their presence would provide compelling evidence for propulsion mechanisms beyond conventional physics. The psychological preparation within the scientific community reflects awareness that December 19th could fundamentally challenge humanity's understanding of its place in the universe. Senior researchers express private concerns about maintaining objectivity when confronting data that might overturn decades of established theory. Younger scientists appear more open to extraordinary interpretations, but also more susceptible to premature conclusions based on incomplete information. This generational divide adds complexity to an already unprecedented situation. Data security measures for December 19th observations have reached levels typically reserved for national defense operations. Multiple encryption layers protect information transmission between facilities. Access to real-time data has been restricted to essential personnel with appropriate security clearances. Analysis will occur in isolated computing environments with no external network connections to prevent unauthorized disclosure of potentially sensitive findings. The backup observation systems include experimental instruments not typically used for astronomical research. Synthetic aperture radar arrays designed for satellite tracking have been reconfigured for deep space observation. Quantum sensors developed for fundamental physics experiments offer detection capabilities that extend far beyond conventional telescopes. These specialized tools could reveal characteristics of 3I Atlas that remain invisible to standard observational methods. Weather monitoring has intensified across all observation sites, with meteorologists providing continuous updates on atmospheric conditions that could affect data quality. Cloud cover, atmospheric turbulence, and precipitation patterns are being tracked with precision typically reserved for hurricane forecasting. Mobile telescope systems stand ready for rapid deployment to alternate locations if primary sites experience adverse conditions during the critical observation window. The spectroscopic analysis planned for December 19th will examine expelled material with resolution capabilities that can identify individual molecular species and their formation processes. This chemical fingerprinting could reveal whether the jets contain compounds requiring specific production methods or processing technologies. Natural sublimation creates predictable gas mixtures based on original ice composition. Artificial propulsion systems would likely show very different signatures, potentially including synthetic compounds or isotopic ratios that don't occur naturally. Timing measurements will achieve precision levels capable of detecting velocity changes measured in centimeters per second. This sensitivity could reveal whether 3i Atlas makes systematic trajectory adjustments, indicating active navigation rather than purely ballistic motion. Natural outgassing creates thrust in random directions that tend to average out over time. Controlled propulsion would demonstrate systematic velocity changes correlating with specific operational patterns. The observation protocol incorporates automated systems that will flag anomalies for immediate human attention. Machine learning algorithms trained on both natural comet behavior and theoretical artificial signatures will process incoming data in real time, alerting researchers to patterns requiring immediate follow-up observations. These artificial intelligence systems can identify subtle correlations between different measurement types that human analysts might miss during intense observation periods. International cooperation faces unprecedented challenges as different nations approach the 3i Atlas phenomenon with varying levels of openness and security concerns. Some countries have restricted access to their most sensitive detection equipment, limiting collaborative observation scope. Others insist on independent verification of all data before sharing results. The scientific ideal of open collaboration encounters the reality that potential evidence of extraterrestrial technology carries implications extending far beyond academic interest. The media management strategy reflects careful consideration of how extraordinary findings might affect public perception and social stability. Press releases have been prepared for multiple scenarios, with language crafted to inform without causing panic or uncontrolled speculation. The challenge involves communicating complex scientific uncertainties while acknowledging the profound implications various outcomes could have for humanity's understanding of its cosmic significance. Public interest monitoring systems track social media discussions and news coverage to assess public readiness for different types of announcements. Communication specialists analyze sentiment patterns and prepare targeted messaging strategies for various discovery scenarios. These efforts aim to inform the public accurately, while preventing misinformation that could complicate official responses to extraordinary findings. The final equipment calibrations will verify that every system operates at optimal performance levels. These checks encompass not just primary observation instruments, but also data recording systems, communication networks, and backup power supplies maintaining the entire operation. Calibration procedures exceed normal requirements because December 19th represents a singular opportunity that cannot be repeated if technical problems compromise data quality. Advanced simulation systems continue running scenarios for every possible observation outcome. These models incorporate not just the physics of potential fragmentation or continued coherence, but also the sociological and political ramifications of different discovery results. The simulations help decision-makers prepare for scenarios ranging from confirmation of exotic natural phenomena to evidence of artificial intelligence operating beyond our solar system. The energy signature monitoring has revealed patterns that don't match any known natural electromagnetic processes. The consistency of these signatures suggests either remarkable self-organization in natural systems or active control mechanisms maintaining specific operational parameters despite changing environmental conditions. This stability, across varying solar radiation intensities and gravitational influences, points towards sophisticated regulatory systems. Quantum interference patterns detected in radio observations have attracted attention from physicists working on advanced communication technologies. The patterns resemble theoretical predictions for quantum encrypted data transmission across interstellar distances. While natural quantum effects can occur in space environments, the coherence and structure observed around 3i Atlas exceed what random processes typically produce. The debris field analysis, should fragmentation occur, will require tracking potentially millions of individual particles across vast regions of space. Computer models predict that natural breakup would create specific dispersal patterns based on fragment size, velocity, and the forces acting upon them. This debris tracking could continue for months or years, requiring sustained international cooperation and resource allocation that extends far beyond the December 19th observation window. Satellite operators have been quietly briefed on potential risks from debris fields that could affect Earth-orbiting infrastructure. While 3i Atlas trajectory poses no direct collision threat to our planet, fragmentation could create high-velocity particles that might intersect satellite orbits months or years in the future. Tracking systems are being upgraded to monitor potential long-term hazards from any debris that might result from structural failure. The orbital mechanics team has identified another anomaly that adds to the growing list of unexplained characteristics. 3. iAtlas shows micro-corrections that appear to compensate for perturbations before they fully manifest. Small gravitational influences from outer planets should gradually alter the object's path over time, yet these effects seem to be countered by precisely timed adjustments in jet orientation and intensity. Atmospheric monitoring equipment has detected minute disturbances in Earth's upper atmosphere that correlate with 3i Atlas activity cycles. While the object remains hundreds of millions of kilometers away, sensitive magnetosphere sensors record fluctuations that align with the rhythmic patterns observed in jet emissions. These correlations suggest that 3i Atlas influence extends beyond its immediate vicinity through electromagnetic fields or particle streams interacting with Earth's magnetic environment. The December 19th timeline has been choreographed with precision rivaling military operations. Every participating facility will follow synchronized protocols designed to maximize data collection, while minimizing conflicts between different observation requirements. Coordination involves telescopes across multiple continents operating in different time zones, requiring communication systems maintaining split-second timing accuracy across global distances. Contingency plans for equipment failures include rapid deployment of backup systems and real-time switching between primary and secondary observation platforms. Mobile telescopes have been positioned at strategic locations with ability to relocate quickly if atmospheric conditions or technical problems compromise primary sites. Backup systems include experimental instruments not typically used for astronomical observations, such as synthetic aperture radar arrays and quantum sensors developed for fundamental physics research. The data analysis pipeline incorporates artificial intelligence systems trained specifically on 3i Atlas behavior patterns. These tools can process incoming observations in real time, flagging anomalies and potential artificial signatures faster than human analysts could identify them. Machine learning algorithms have been trained on theoretical models of both natural comet behavior and hypothetical artificial propulsion systems, enabling rapid classification of observed phenomena. Weather contingency plans have been activated worldwide, with meteorologists providing continuous atmospheric condition updates at every major observation site. Backup facilities in different climate zones stand ready to assume primary observation responsibilities if weather compromises optimal locations. The December 19th window allows some timing flexibility, but atmospheric conditions could significantly impact data quality if primary sites experience adverse weather. International agreements governing the sharing and disclosure of December 19th findings remain classified, but their existence suggests world leaders recognize the potential significance of discoveries. These agreements presumably address how different findings would be announced, what information would be shared publicly versus kept confidential, and how international cooperation would continue if 3i Atlas proves to be of artificial origin. The scientific community has prepared for multiple outcome scenarios, each requiring different types of follow-up investigations and public communications. If 3i Atlas is fragmented, researchers will focus on tracking debris patterns and analyzing the physics of structural failure under extreme conditions. If the object remains intact and active, investigation will shift toward understanding propulsion mechanisms and energy sources exceeding current theoretical frameworks. Public communication strategies have been developed with carefully crafted language designed to inform without causing panic or premature speculation. The challenge lies in communicating scientific uncertainty while acknowledging profound implications various discoveries could have for humanity's understanding of its place in the universe. Educational materials have been prepared to help the public understand both the technical aspects of the observations and their potential significance. The countdown continues toward December 19th, with 3i Atlas maintaining extraordinary behavior patterns despite increasing distance from the Sun. The object's persistence in producing massive organized jets well beyond the point where natural sublimation should have ceased adds urgency to upcoming observations. Whatever mechanism drives this phenomenon has demonstrated remarkable endurance and consistency, characteristics pointing toward either physics we don't understand or engineering we haven't achieved. Final system checks scheduled for December 18th include verification procedures exceeding normal operational requirements. Every system participating in the observation campaign will undergo comprehensive testing to ensure optimal performance during the critical observation window. These preparations include backup power systems, redundant data recording capabilities, and communication links maintaining coordination even if primary networks experience disruptions. The technical coordination required has exposed limitations in global space monitoring infrastructure that few anticipated. Telescopes designed for specific research programs don't easily integrate into coordinated observation campaigns. Data formats vary between institutions, communication protocols differ across agencies, and timing synchronization becomes critical when every second could provide crucial information. Engineers have been developing solutions to make systems work together that were never designed for this level of cooperation. Advanced computer modeling systems have been running continuous simulations attempting to predict every possible outcome for December 19th observations. These models incorporate thousands of variables, from structural integrity under various stress conditions to dispersal patterns expected if catastrophic fragmentation occurs. What emerges from these calculations presents a stark choice between witnessing the spectacular death of an exotic comet or confirming that something far more extraordinary has been travelling through our solar system. The universe has delivered 3i Atlas to our doorstep at precisely the moment when our technology is barely adequate to study it properly. This convergence of cosmic timing and human capability suggests we stand at a threshold, ready to learn truths about reality that previous generations could only imagine. December 19th will determine whether we're prepared for those truths and what we'll do with them once they're revealed. The final preparations continue as the most significant astronomical observation in human history approaches. Within hours, we'll know whether we're alone in our ability to travel between the stars, or whether the universe contains intelligence that has been watching us long before we developed the tools to watch back. The answers await, and with them, the transformation of everything we thought we knew about our place in the cosmos. The electromagnetic signature analysis has unveiled patterns that stretch the boundaries of conventional physics. Deep space monitoring arrays, originally designed to track satellite communications and solar radiation, have detected structured emissions emanating from 3i Atlas that follow mathematical progressions, rather than the random fluctuations expected from natural phenomena. These signals pulse in precise intervals that mirror the object's jet activity, creating a synchronized electromagnetic and physical display that no known natural process can adequately explain. Radio telescopes across 3 continents have independently confirmed the presence of these organized transmissions, ruling out equipment malfunction or atmospheric interference. The signals operate across multiple frequency bands simultaneously, maintaining coherent phase relationships that would require either exotic natural resonance or active transmission systems. Most unsettling is the apparent modulation of these emissions based on solar activity, as if 3i Atlas is actively monitoring and responding to changes in our star's electromagnetic output. The thermal regulation displayed by this object continues to defy every model of heat distribution in space environments. While natural bodies should show dramatic temperature variations between sun-facing and shadow sides, 3i Atlas maintains remarkably uniform surface temperatures through mechanisms that remain completely unexplained. Infrared imaging reveals heat patterns that migrate across the surface in coordinated waves, suggesting internal systems capable of redistributing thermal energy with precision that exceeds any known natural process. This thermal management becomes even more remarkable when considered alongside the object's sustained activity levels. The energy required to maintain current jet output while regulating surface temperature would exhaust any conventional energy storage system within days. Yet 3i Atlas has maintained this performance for months, drawing upon power sources that either violate our understanding of energy conservation or operate through principles that current physics cannot describe. Gravitational analysis using the most sensitive instruments available has revealed mass distribution patterns that don't align with the object's visible structure. Pulsar timing measurements detect gravitational perturbations, suggesting a much denser core than optical observations would indicate, as if the majority of 3i Atlas mass is concentrated in regions invisible to our detection methods. This mass configuration resembles engineered structures more than natural aggregations of ice and rock. the precision of the object's trajectory corrections has attracted attention from orbital mechanics specialists who normally focus on spacecraft navigation rather than comet behavior. 3. iAtlas demonstrates course adjustments that anticipate gravitational influences before they become significant, making tiny velocity changes that maintain its path with accuracy exceeding the best human navigation systems. These corrections occur with timing that suggests either remarkable coincidence or predictive algorithms operating in real time. Advanced spectroscopic analysis of the expelled material has identified molecular combinations that shouldn't exist in natural comet compositions. Complex carbon chains appear in concentrations that require specific formation conditions not found in typical ice sublimation processes. The isotopic ratios of key elements fall outside ranges documented in solar system materials, suggesting either exotic formation environments or processing through mechanisms unknown to current chemistry. The international response to these findings has shifted from scientific curiosity to strategic concern, as government agencies recognize the potential implications of confirming artificial origin. Military satellite networks have been quietly repositioned to provide redundant tracking capabilities. Communication protocols between major space agencies now include encryption methods, typically reserved for national security operations. The transformation of routine astronomical observation into classified monitoring reflects understanding that December 19th could produce information affecting global stability. Security measures surrounding the observation campaign have reached unprecedented levels for civilian scientific research. Data transmission between facilities now flows through multiple encryption layers. Access to real-time observations has been restricted to personnel with appropriate clearances. Analysis will occur in isolated computing environments to prevent unauthorized disclosure of potentially sensitive findings. These precautions suggest that decision-makers are preparing for discoveries that extend far beyond academic interest. The backup observation systems deployed for December 19th include experimental technologies not typically used for astronomical research. Quantum interferometry arrays designed for gravitational wave detection offer sensitivity that could reveal structural details invisible to conventional telescopes. Synthetic aperture radar systems provide imaging capabilities that don't depend on reflected light, potentially showing internal features or surface characteristics that optical methods cannot detect. Weather monitoring has intensified to levels typically reserved for hurricane tracking, with meteorological teams providing continuous updates on atmospheric conditions at every observation site worldwide. Cloud formation patterns, atmospheric turbulence levels, and precipitation forecasts are being analyzed with precision that acknowledges the singular nature of this opportunity. Mobile telescope systems stand ready for rapid deployment to alternate locations if primary sites experience adverse conditions during critical observation windows. The spectroscopic analysis planned for December 19th will examine expelled material with resolution capabilities that can identify individual molecular species and trace their formation processes. This chemical fingerprinting could reveal whether the jets contain compounds requiring specific production methods or processing technologies that don't occur naturally. The distinction between natural sublimation signatures and potential propulsion system exhaust could provide definitive evidence about 3iAtlas' true nature. Timing measurements will achieve precision levels capable of detecting velocity changes measured in millimeters per second. Sensitivity that could reveal systematic trajectory adjustments indicating active navigation rather than purely ballistic motion. Natural outgassing creates thrust in random directions that tend to average out over time, while controlled propulsion would show systematic velocity patterns correlating with specific operational cycles or environmental responses. The observation protocol incorporates machine learning systems that will process incoming data in real time, automatically flagging patterns that require immediate human attention. These artificial intelligence tools have been trained on both natural comet behavior and theoretical signatures of advanced propulsion systems, enabling rapid classification of observed phenomena during the intense observation period when human analysts might miss subtle correlations between different types of measurements. International cooperation faces challenges as different nations balance scientific collaboration with security concerns about potentially sensitive discoveries. Some countries have restricted access to their most advanced detection equipment, limiting the scope of collaborative observations. Others require independent verification of all data before sharing results with international partners. The tension between open scientific inquiry and national security interests creates complications that most researchers have never encountered. The media management strategy reflects careful consideration of how extraordinary findings might be received by a global public unprepared for confirmation that we are not alone in developing interstellar travel capabilities. Press releases have been prepared for multiple scenarios, with language carefully crafted to inform without causing panic or uncontrolled speculation. Communication specialists have analysed public sentiment patterns and developed targeted messaging approaches for various discovery outcomes. Public interest monitoring systems track social media discussions and news coverage to assess readiness for different types of announcements. The goal involves informing the public accurately while preventing misinformation that could complicate official responses to extraordinary findings. Educational materials have been prepared to help non-scientists understand both the technical aspects of the observations and their potential implications for humanity's understanding of its place in the universe. The final equipment calibrations, scheduled for December 18th, will verify that every system operates at peak performance levels during the critical observation window. These checks encompass primary observation instruments, data recording systems, communication networks, and backup power supplies that maintain the entire operation. Calibration procedures exceed normal requirements because December 19th represents an unrepeatable opportunity that could be compromised by any technical failures. Advanced simulation systems continue processing scenarios for every possible observation outcome, incorporating not just the physics of potential fragmentation or continued coherence, but also the sociological and political ramifications of different discovery results. These models help decision-makers prepare for scenarios ranging from confirmation of exotic natural phenomena to evidence of technology from civilizations beyond our solar system. The energy signature monitoring reveals electromagnetic patterns that maintain consistency despite changing environmental conditions, suggesting either remarkable self-organization in natural systems or active control mechanisms that regulate operational parameters. This stability across varying solar radiation intensities and gravitational influences points towards sophisticated regulatory systems that exceed anything found in natural materials or processes. Quantum interference patterns detected in radio observations resemble theoretical predictions for advanced communication technologies, showing coherence and structure that exceed what random natural processes typically produce. While quantum effects can occur in space environments, the organized nature of these patterns suggests either exotic physics or engineered systems operating according to principles that current human technology is only beginning to explore. The debris field analysis protocols, should fragmentation occur, will require tracking potentially millions of individual particles across vast regions of space using computational resources that exceed most institutional capabilities. International networks have been established to share processing power and coordinate tracking efforts that could continue for months or years, requiring sustained cooperation and resource allocation, extending far beyond the December 19th observation window. Satellite operators have been briefed on potential risks from debris fields that might affect Earth-orbiting infrastructure in the future. While 3I Atlas trajectory poses no direct collision threat to our planet, fragmentation could create high-velocity particles that intersect satellite orbits months or years later. Tracking systems are being upgraded to monitor long-term hazards from any debris resulting from structural failure during the solar encounter. The orbital mechanics analysis has identified micro-corrections that appear to compensate for gravitational perturbations before they fully manifest, suggesting navigation systems capable of predicting and countering influences from outer planets with timing precision that exceeds current human spacecraft capabilities. These adjustments occur through precisely coordinated changes in jet orientation and intensity that maintain trajectory accuracy despite complex gravitational environments. Atmospheric monitoring equipment has detected minor disturbances in Earth's upper atmosphere that correlate with 3I Atlas activity cycles, even though the object remains hundreds of millions of kilometers away. Sensitive magnetosphere sensors record fluctuations that align with rhythmic patterns in jet emissions, suggesting that the object's influence extends beyond its immediate vicinity through electromagnetic fields or particle streams that interact with our planet's magnetic environment. The December 19th observation timeline has been synchronized across multiple time zones with precision that rivals military coordination, ensuring seamless coverage as Earth's rotation changes optimal viewing angles for different facilities. Communication systems maintain split-second timing accuracy across global distances, enabling real-time coordination between telescopes that must work together during narrow observation windows. Contingency plans for equipment failures include rapid deployment of backup systems and automated switching between primary and secondary observation platforms. Mobile telescopes positioned at strategic locations can relocate quickly if atmospheric conditions or technical problems compromise primary sites. Emergency protocols exist for scenarios where observations might reveal immediate threats or require rapid follow-up measurements using specialized equipment not typically employed for astronomical research. The data analysis pipeline incorporates distributed computing networks that can process the expected flood of information from dozens of instruments simultaneously. The computational power required to analyze spectroscopic data, imaging sequences, gravitational measurements, and electromagnetic signatures in real time exceeds the capacity of individual research institutions, requiring international cooperation in both observation and analysis phases. Weather contingency plans activated worldwide provide continuous atmospheric updates at every major observation site, with backup facilities in different climate zones ready to assume primary responsibilities if conditions compromise optimal locations. The December 19th window allows some timing flexibility, but atmospheric interference could significantly impact data quality if primary sites experience adverse weather during critical observation periods. International agreements governing the sharing and disclosure of December 19th findings remain classified, but their existence indicates that world leaders recognize the potential significance of what might be discovered. These agreements presumably address how different types of findings would be announced, what information would be shared publicly versus kept confidential, and how international cooperation would continue if 3i Atlas proves to be of artificial origin. The scientific community has prepared response protocols for multiple outcome scenarios, each requiring different types of follow-up investigations and public communications. If 3i Atlas is fragmented, research will focus on debris tracking and structural failure analysis under extreme conditions. If the object remains intact and active, investigation will shift toward understanding propulsion mechanisms and energy sources that exceed current theoretical frameworks, potentially revolutionizing our understanding of physics and engineering. The psychological preparation extends beyond technical readiness to include counseling resources for researchers who might struggle with implications of their findings. The possibility that humanity is not alone in developing interstellar travel capabilities challenges fundamental assumptions about our uniqueness and significance in the universe. Support systems have been established to help personnel process discoveries that could reshape human understanding of reality itself. Advanced data security protocols protect information transmission, with encryption methods typically reserved for national defense operations. Real-time analysis will occur in isolated computing environments with no external network connections, preventing unauthorized access to potentially sensitive findings. Multiple independent teams will verify results before any public announcements, ensuring accuracy while maintaining appropriate security for information that could have profound implications for global stability. The final countdown approaches as 3i Atlas continues its outbound journey, maintaining extraordinary behavior patterns that have persisted well beyond the point where natural processes should have exhausted available energy sources. The object's remarkable consistency in producing massive organized jets, despite increasing distance from solar heating, adds urgency to the upcoming observations and reinforces the critical importance of determining whether we're witnessing exotic natural phenomena or our first confirmed encounter with technology from beyond our solar system. December 19th will provide answers to questions that have driven months of investigation and preparation. The observations will either confirm that the universe contains natural processes far stranger than we previously imagined, or provide evidence that intelligence capable of interstellar travel has visited our solar system. Either outcome promises to transform our understanding of reality itself, marking a moment when humanity's relationship with the cosmos changes permanently. The stage is set for what may prove to be the most consequential observation in human history. Within days, we'll discover whether 3i Atlas represents the most exotic comet ever documented, or confirmation that we are not alone in our ability to send objects between the stars. The universe has delivered this mystery to our doorstep, at precisely the moment when our technology has become barely adequate to solve it, suggesting that we stand at a threshold between old certainties and new realities that will define how future generations understand their place in a cosmos that may be far more populated and technologically active than we ever dared to imagine. Imagine! The technical infrastructure supporting December 19th observations represents the largest coordinated astronomical effort in modern history. Communication networks spanning 6 continents have been synchronized to millisecond precision, enabling real-time data sharing between facilities that were never designed to operate as unified systems. The complexity of this coordination becomes apparent when considering that telescopes optimized for deep space observation must now track a rapidly moving target, while maintaining focus stability across varying atmospheric conditions. Ground-based radar installations have been reconfigured to provide backup tracking capabilities that don't depend on optical visibility. These systems can detect position changes measured in kilometers across hundreds of millions of kilometers of space, offering the precision needed to distinguish between passive drift and active navigation. The radar signatures from 3i Atlas have shown characteristics that don't match typical solid body reflections, instead suggesting internal structures with multiple density layers and possibly hollow regions that resemble engineered compartments more than natural ice and rock distributions. The electromagnetic monitoring campaign has expanded to cover frequency ranges far beyond standard astronomical observation protocols. Military communication satellites have been temporarily repurposed to search for structured signals that might indicate data transmission or operational commands. Deep space monitoring arrays, originally designed for tracking spacecraft communications, now focus on 3i Atlas, scanning for any organized emissions that could suggest active systems rather than random natural phenomena. Spectroscopic analysis capabilities have been pushed to theoretical limits, with multiple facilities coordinating to capture chemical signatures across the entire electromagnetic spectrum simultaneously. The goal involves identifying not just what materials are being expelled, but how those materials are being processed and organized. Natural sublimation creates predictable gas mixtures based on original composition, while artificial propulsion systems would likely show very different signatures, potentially including synthetic compounds or unusual molecular structures that don't occur in natural ice formations. The gravitational measurement systems deployed for December 19th include experimental technologies that operate at the edge of current detection capabilities. Pulsar timing arrays can potentially reveal mass distributions that optical observations cannot detect, providing independent verification of the object's true structural characteristics. These measurements could distinguish between natural density variations and engineered mass concentrations that might indicate internal machinery, or propulsion systems operating within the visible exterior. International space law experts have been working quietly to develop frameworks that could govern the study of potentially artificial objects discovered in our solar system. The existing treaty structure contains no provisions for encounters with technology from other civilizations, creating legal ambiguities that could complicate international cooperation if extraordinary findings emerge. Diplomatic channels have been established to coordinate responses that balance scientific transparency with security concerns that might arise from confirming non-human intelligence. The psychological preparation within the scientific community reflects awareness that December 19th observations could challenge fundamental assumptions about humanity's place in the universe. Research teams have access to counseling resources designed to help process discoveries that might revolutionize our understanding of reality itself. The possibility that we are not alone in developing interstellar travel capabilities carries implications that extend far beyond academic interest, potentially affecting everything from religious beliefs to geopolitical relationships. Data processing systems have been configured to handle information volumes that exceed normal astronomical observation capabilities. Distributed computing networks spanning multiple institutions will analyze spectroscopic data, imaging sequences, and electromagnetic signatures simultaneously, searching for patterns that might indicate artificial origin. Machine learning algorithms trained on both natural phenomena and theoretical technological signatures will flag anomalies requiring immediate human attention during the critical observation period. Security protocols for information handling have reached levels typically reserved for national defense operations. Data, Transmission between facilities now flows through multiple encryption layers designed to prevent unauthorized access to potentially sensitive findings. Real-time analysis will occur in isolated computing environments with no external network connections, ensuring that preliminary results remain secure until proper verification can be completed through established scientific review processes. The observation timeline has been choreographed to account for Earth's rotation and optimal viewing angles from different geographic locations. As 3i Atlas moves through its closest approach, different telescopes will have peak observation conditions at different times, requiring seamless coordination between facilities as viewing opportunities shift around the globe. Communication systems maintain synchronization that enables instant handoffs between observation sites as atmospheric conditions and equipment capabilities change throughout the critical observation window. Weather monitoring has intensified to unprecedented levels, with meteorological teams providing continuous updates on atmospheric conditions that could affect observation quality at every major telescope facility worldwide. Backup sites in different climate zones stand ready to assume primary observation responsibilities if cloud cover, atmospheric turbulence, or precipitation compromises planned observation locations. Mobile telescope systems have been positioned for rapid deployment to alternate sites if primary facilities experience adverse conditions during crucial measurement periods. The debris field analysis protocols, should fragmentation occur, will require tracking potentially millions of individual particles across vast regions of space using computational resources that exceed most institutional capabilities. Computer models predict specific dispersal patterns based on fragment size, velocity, and environmental forces, enabling researchers to distinguish between natural breakup signatures and patterns that might indicate controlled separation of artificial components. This analysis could continue for months or years, requiring sustained international cooperation and resource allocation. Advanced simulation systems continue processing scenarios for every possible observation outcome, incorporating not just the physics of structural failure or continued coherence, but also the sociological and political ramifications of different discovery results. These models help decision-makers prepare for situations ranging from confirmation of exotic natural processes to evidence of technology from civilizations beyond our solar system, each requiring very different response protocols and communication strategies. The technical challenges extend beyond simply pointing instruments at the correct coordinates. 3i Atlas will be moving at tremendous velocity relative to Earth, requiring tracking algorithms that can maintain focus while compensating for atmospheric distortion and equipment limitations. Brightness variations could occur unpredictably if structural changes happen during observation, demanding rapid adjustments to exposure settings and filter configurations across multiple facilities simultaneously. Emergency response procedures have been established for scenarios where observations might reveal immediate threats or require rapid follow-up measurements using specialized equipment not typically employed for astronomical research. Mobile radar systems can be deployed quickly to locations with optimal tracking conditions. Communication protocols exist for coordinating international responses to unexpected discoveries that might demand immediate action rather than leisurely scientific analysis over extended time periods. The energy signature analysis has revealed electromagnetic patterns that maintain remarkable consistency despite changing environmental conditions, suggesting either sophisticated self-organization in natural systems or active control mechanisms that regulate operational parameters with precision exceeding known material properties. This stability across varying solar radiation intensities and gravitational influences points toward regulatory systems that operate according to principles that current physics struggles to explain through natural processes alone. Quantum interference patterns detected in radio observations of 3i Atlas resemble theoretical predictions for advanced communication technologies, showing coherence and organizational structure that exceed what random natural processes typically produce. While quantum effects can occur naturally in space environments, the specific patterns observed around this object suggest either exotic physics, operating at macroscopic scales, or engineered systems that utilize quantum principles for information processing or transmission across interstellar distances. The orbital mechanics team has documented micro-corrections that appear to anticipate gravitational influences before they become significant, suggesting navigation capabilities that exceed current human spacecraft technology. These adjustments occur through precisely coordinated changes in jet orientation and intensity, maintaining trajectory accuracy that would require predictive algorithms and response systems operating with computational sophistication that challenges our understanding of what natural processes can achieve. Atmospheric monitoring equipment has detected minute disturbances in Earth's upper atmosphere that correlate with 3I Atlas activity cycles, despite the object remaining hundreds of millions of kilometers away from our planet. Sensitive magnetosphere sensors record fluctuations that align with rhythmic patterns observed in jet emissions, indicating that the object's influence extends beyond its immediate vicinity through electromagnetic fields or particle streams that interact with Earth's magnetic environment in measurable ways. The mass distribution analysis using gravitational measurements has revealed characteristics that don't align with natural comet structures. Dense core regions appear concentrated in specific locations rather than distributed uniformly throughout the object, creating gravitational signatures that resemble engineered configurations more than random aggregations of ice and rock. These measurements provide independent verification of structural characteristics that optical observations cannot directly detect. Thermal regulation patterns continue to defy conventional heat distribution models for objects in space environments. While natural bodies should display dramatic temperature variations between sun-facing and shadow regions, 3I Atlas maintains remarkably uniform surface temperatures through mechanisms that remain completely unexplained by known physics. Heat patterns migrate across the surface in coordinated waves, suggesting internal systems capable of redistributing thermal energy with precision that exceeds any documented natural process. The chemical composition analysis of expelled material has identified molecular combinations that require specific formation conditions not found in typical ice sublimation processes. Complex carbon chains appear in concentrations suggesting active chemical processing rather than passive vaporization of existing compounds. Isotopic ratios of key elements fall outside ranges documented in solar system materials, indicating either exotic formation environments or processing through mechanisms that current chemistry cannot adequately explain. International cooperation continues despite tensions created by security concerns about potentially sensitive discoveries. Some nations have restricted access to their most advanced detection equipment, while others require independent verification of all data before sharing results with international partners. The balance between open scientific collaboration and national security interests creates operational complications that most researchers have never encountered in their professional careers. The media management strategy has been developed with careful consideration of how extraordinary findings might affect public perception and social stability worldwide. Communication specialists have prepared targeted messaging approaches for various discovery scenarios, with language designed to inform accurately while preventing panic or uncontrolled speculation that could complicate official responses to unprecedented findings about our place in the universe. The final system check scheduled for December 18th will verify that every component operates at peak performance during the critical observation window. These comprehensive tests encompass primary observation instruments, data recording systems, communication networks, and backup power supplies that maintain the entire operation. Equipment calibration procedures exceed normal operational requirements because December 19th represents an unrepeatable opportunity that could be compromised by any technical failures during crucial measurement periods. Public interest monitoring systems continue tracking social media discussions and news coverage to assess global readiness for different types of announcements about 3I Atlas findings. Educational materials have been prepared to help non-scientists understand both the technical aspects of the observations and their potential implications for humanity's understanding of its cosmic significance, regardless of whether discoveries confirm exotic natural phenomena or something far more extraordinary. The countdown approaches its final phase as 3I Atlas maintains behavior patterns that have persisted well beyond the point where natural processes should have exhausted available energy sources. The object's extraordinary consistency in producing massive, organized jets, despite increasing distance from solar heating, reinforces the critical importance of determining whether we're witnessing the most extreme natural phenomena ever documented, or our first confirmed encounter with intelligence that has mastered interstellar travel. December 19th will provide definitive answers to questions that have driven months of unprecedented international scientific cooperation and resource allocation. The observations will either demonstrate that the universe contains natural processes far stranger than we previously comprehended, or confirm that we are not alone in our ability to create technology capable of traversing the vast distances between stars. Either outcome promises to transform our understanding of reality itself. The universe has delivered this mystery to our doorstep at precisely the moment when our technological capabilities have become barely adequate to solve it. This convergence suggests that we stand at a threshold between familiar certainties and revelations that will define how future generations understand their relationship with a cosmos that may contain intelligence and technology far beyond what we have achieved or even imagined possible. The final hours before December 19th have transformed what began as routine astronomical observation into the most scrutinized scientific event of our generation. Research facilities that normally operate in quiet isolation now find themselves at the center of a global effort that spans continents and involves resources typically reserved for detecting the most fundamental forces in the universe. The magnitude of this coordination reflects not merely scientific curiosity, but recognition that we may be approaching a moment that redefines humanity's understanding of its place in the cosmic order. Within the scientific community, the atmosphere has shifted from academic excitement to something approaching existential tension. Senior researchers who have spent decades studying the predictable behavior of comets and asteroids now face data that refuses to conform to any established model. The mathematical frameworks that have guided astrophysics for generations consistently point toward conclusions that challenge the fundamental distinction between natural and artificial phenomena in ways that make even the most experienced scientists uncomfortable. The energy output calculations have reached a point where conventional explanations strain credibility beyond reasonable limits. 3I Atlas continues to expel material at rates that would require power sources exceeding anything known to exist in natural systems. The sustained nature of this activity, maintained across months of observation, suggests either exotic physics that we have yet to discover or active systems that manage energy with efficiency that surpasses our current understanding of what matter can achieve without deliberate organization and control. Technical teams working around the clock have pushed detection equipment to performance levels that exceed design specifications. Instruments built to observe distant galaxies must now track a rapidly moving target with precision that demands constant recalibration and adjustment. The complexity of coordinating these systems across multiple time zones while maintaining data integrity has created operational challenges that dwarf any previous astronomical observation campaign. The electromagnetic signature monitoring has revealed structured patterns that persist despite changing environmental conditions, displaying a level of organization that natural processes struggle to explain. These signals operate across multiple frequency bands simultaneously, maintaining phase relationships that would require either remarkable coincidence or active coordination between different emission sources. The mathematical precision of these patterns resembles engineered communication systems more than random natural phenomena. Security protocols surrounding the observation campaign have evolved to include measures typically reserved for matters of national importance. Data transmission between facilities now incorporates encryption methods that reflect understanding that December 19th findings could carry implications extending far beyond academic research. The transformation of scientific observation into classified monitoring demonstrates that decision-makers at the highest levels are preparing for outcomes that could affect global perspectives on humanity's cosmic significance. International cooperation faces unprecedented challenges as different nations balance scientific collaboration with concerns about potentially sensitive discoveries. Access to the most advanced detection equipment has been restricted in some cases, while others have implemented independent verification requirements that slow the collaborative process. The tension between open scientific inquiry and national security interests creates complications that most researchers have never encountered in their professional careers. The observation protocol incorporates artificial intelligence systems designed to process incoming data in real time and identify patterns that might indicate characteristics beyond natural comet behavior. These machine learning algorithms have been trained on both conventional astronomical phenomena and theoretical signatures that advanced technology might produce, enabling rapid analysis during the critical observation window when human analysts might miss subtle correlations between different types of measurements. Weather monitoring has reached intensity levels typically reserved for tracking major storm systems, with meteorological teams providing continuous updates on atmospheric conditions at observation sites worldwide. The singular nature of this opportunity means that cloud cover, atmospheric turbulence, or precipitation at key facilities could compromise data collection that cannot be repeated. Backup sites in different climate zones stand ready to assume primary responsibilities if conditions deteriorate at planned observation locations. The gravitational analysis planned for December 19th will employ the most sensitive measurement techniques available, potentially revealing mass distributions that optical observations cannot detect directly. These measurements could distinguish between natural density variations and engineered mass concentrations that might indicate internal systems operating within the visible exterior structure. The precision required for these measurements pushes current detection capabilities to their absolute limits. Debris field analysis protocols have been established for the possibility that 3i Atlas has fragmented under the extreme conditions of its solar encounter. Computer models predict specific dispersal patterns based on fragment size and environmental forces, enabling researchers to distinguish between natural breakup signatures and patterns that might suggest controlled separation of artificial components. This analysis could require tracking millions of individual particles across vast regions of space for extended periods. The spectroscopic examination will analyze expelled material with resolution capabilities that can identify individual molecular species and trace their formation processes. This chemical fingerprinting could reveal whether the jets contain compounds that require specific production methods or processing technologies that don't occur naturally. The distinction between sublimation signatures and potential propulsion system exhaust could provide definitive evidence about the object's true nature. Advanced simulation systems continue processing scenarios for every conceivable observation outcome, incorporating not just the physics of potential structural failure or continued coherence, but also the sociological and political ramifications of different discovery results. These models help decision-makers prepare for situations that could range from confirmation of exotic natural processes to evidence of technology from civilizations beyond our solar system. The psychological preparation within the research community reflects awareness that December 19th observations could fundamentally challenge assumptions about the uniqueness of human technological achievement. Support systems have been established for personnel who might struggle with implications of discoveries that revolutionize our understanding of intelligence and capability in the universe. The possibility that we are not alone in developing interstellar travel technology carries philosophical and emotional dimensions that extend far beyond scientific interest. Data security measures have reached levels that transform routine astronomical research into classified operations. Real-time analysis will occur in isolated computing environments with no external network connections, preventing unauthorized access to potentially sensitive findings. Multiple independent teams will verify results before any public announcements, ensuring accuracy while maintaining appropriate security for information that could have profound implications for global stability and human self-perception. Public communication strategies have been developed with careful consideration of how extraordinary findings might be received by populations unprepared for confirmation that advanced technology operates beyond our solar system. Educational materials have been prepared to help non-scientists understand both the technical aspects of the observations and their potential significance for humanity's cosmic perspective, regardless of whether discoveries confirm natural phenomena or something far more extraordinary. The orbital mechanics team continues documenting trajectory adjustments that appear to anticipate gravitational influences before they become significant, suggesting navigation capabilities that would require predictive algorithms operating with computational sophistication that challenges current understanding of what natural processes can achieve. These microcorrections occur through precisely coordinated changes in jet behavior that maintain path accuracy with timing that resembles active guidance rather than passive response. Atmospheric monitoring equipment has detected correlations between 3i Atlas activity and disturbances in Earth's upper atmosphere, despite the object's tremendous distance from our planet. These interactions suggest that the object's influence extends beyond its immediate vicinity through electromagnetic fields or particle streams that affect our magnetic environment in measurable ways, creating connections across space that conventional physics struggles to explain through natural mechanisms alone. The thermal regulation displayed by 3i Atlas continues to defy heat distribution models for objects in space environments. Instead of expected temperature gradients from solar heating, the object maintains uniform surface temperatures through processes that remain completely unexplained. Heat patterns migrate across the surface in coordinated waves, indicating internal systems capable of redistributing thermal energy with precision that exceeds any documented natural capability. Emergency response procedures have been established for scenarios where observations might reveal characteristics requiring immediate follow-up measurements using specialized equipment not typically employed for astronomical research. Mobile systems can be deployed rapidly to optimal observation positions, while communication protocols exist for coordinating international responses to unexpected discoveries that might demand immediate action rather than extended analysis periods. The mass distribution analysis has revealed gravitational signatures that don't align with natural comet structures, suggesting dense regions concentrated in specific locations rather than uniform distribution throughout the object. These characteristics create patterns that resemble engineered configurations more than random aggregations of ice and rock, providing independent evidence of structural organization that optical observations cannot directly reveal. As December 19th approaches and the world's most powerful telescopes prepare to turn their collective gaze toward 3i Atlas, we stand at the precipice of discovery that could fundamentally alter our understanding of what travels between the stars. Whether we witness the spectacular death throes of the most exotic comet ever documented, or confirm our first encounter with technology from beyond our solar system, the answers we receive will echo through history and reshape how future generations understand their place in a universe that may be far more populated and technologically advanced than we ever dared imagine.